Hi, my name's Tim Behrens, and I've been asked to speak to you about up-and-coming themes in the neuroscience of reinforcement learning. So this isn't really a tutorial, more supposed to inspire you so that tomorrow you can be right at the state of the art when you start your research. Okay, so hopefully you've emerged from this morning with a cartoon that looks a little bit like this. The cortex, or the clever parts of your brain, walking around moment by moment, forming a representation of the current state of the world. And then through synapses with the striatum, we can compute a prediction of the value of this state of the world. And this value prediction is evaluated in the dopaminergic prediction error, which tells you whether this value prediction was good or bad. And this value prediction and this prediction error is then taken up to change those synapses between the cortex and the striatum so that the striatum makes a better value prediction next time. Cool. So that's a pretty simple cartoon of how RL works in the brain. And in this talk, I'm going to ask various questions which might nuance this cartoon or fill in some details. Okay, so I'm going to have a small section about dopamine. I'm going to ask a couple of questions. Is it really just learning one value for each state? And is it actually even really learning just about a single state? And then I'm going to have a little section, some sections at the end, talking about this bit up here, saying, well, what should we be learning about? What should that state representation look like if we want to do well? Okay, cool. So let's just start with dopamine. Is it learning a single value? And so think about this situation here where we're trying to learn the value for this man or this character who's leaping over this gap. Now, temporal difference learning would say we should just learn one value. What's the average value? For example, the chances of getting over that gap. But actually, the situation is rather more complicated. Actually, there's a distribution of possible values. There's a good chance he'll make it, which will have a very high value. And there's a good chance that he'll fall, which will have a very low value. And perhaps just learning the average of these values won't do very well at all. And in fact, it turns out that just by augmenting a machine learning reinforcement learner so that it learns the whole distribution of these values rather than just the average value, you get dramatically better performances. Okay, so how do you go about learning these value distributions of possible future values? Well, of course, you're trying to learn distributions, so you need different cells to encode different things. So, for example, here, different cells coding different values. And that means you need different cells coding different prediction errors, one for each value. So we need something like this in the prediction errors. We need, when you get an outcome that's here, you need some of your cells, in this case the average one and the pessimistic one, to code a positive prediction error because it's better than they were expecting. But you see, you need other cells, the optimist in this situation, to code a negative prediction error because it's worse than he was expecting. And it turns out you can get this with just a very simple change to temporal difference learning. What you need is you need cells that differentially weight positive and negative outcomes. So here's your traditional TD cell. He's the guy that codes for the average, and he has an equal weight in green and red, an equal slope. He's equally sensitive to positive and negative rewards. But here's your optimist. He's more sensitive. He overweights positive reward prediction errors and he underweights negative ones. And because he counts the positive ones twice, he ends up learning a higher value. Similarly, this guy, your negative one, overweights the negative prediction errors. And so it turns out that if you do that, just that simple scaling effect will give you a representation, will result in a representation of the whole distribution of values. And so do dopamine neurons do something like this? Well, Zeb Kurth-Nelson and Will Dabney and Matt Botvinnik looked in some data that were recorded in Nara Cheetah's lab and found out that they do. So here are a bunch of different dopamine cells plotted in these lines. And they've all got different scalings for positive and negative, and different cells have different biases, which is exactly what you need for this distributional RL. And actually, if you just take those scalings and back infer from the rules of distributional RL what the reward distribution should have been, you can do a really good job of estimating the distribution of rewards that were given to these mice in the Uchida lab by just looking at the dopamine cells. So that's kind of cool. That's showing that really these dopamine cells are trying to compute prediction errors on a distribution of possible values. Okay, so no, it's not just learning a single value, it looks like. Well, what is it just learning about a single state? This is the situation we imagined, a single state of the world. Let's learn about it. Is that a good thing to think about? Well, in order to think about that, we probably have to take a slightly more complicated task. And so here's a task called the Pillars task, which is often studied in Princeton, here by Ilana Witten. And you can see, and so it looks a little bit like this. The animal has to decide whether to go left or right, and it just goes to the side where the most pillars have happened during the run. So it has to integrate the pillars. Okay, so it's difficult. So that's a little bit more complicated than our normal classical conditioning task. But what nevertheless, we can make pretty good predictions about what TD learning would suggest. This is the kind of thing that it would suggest. Well, it would suggest, okay, I'm going to do better when there's a bigger difference between the left and the right in the number of pillars. Because if there's 20 pillars on the left and 1 on the right, it's easy and I'm never going to get it wrong. But if there's 4 on the left and 5 on the right, it's difficult and I'm going to get it wrong quite often. Okay, so the bigger difference between sides, more likely to get it right, so you have more predicted future value. And so that means that a prediction error signal should look a little bit like this. Dopamine cells should all fire together when the difference increases and suppress when that difference decreases. And then, of course, they should fire again at reward because that's a new reward prediction error. Cool. Okay, so is that what they do? Well, they do all fire at reward in this data from Engelhard and Witten. So that's good news. That could be in line with our cartoon. But look at what else they do. Here you can see regressions of all sorts of different aspects of the task onto the activity of these dopamine cells. And so you can see that some of them are just the animals moving their legs, others where they are on the track, etc., etc. And you can see something pretty completely clearly, which is different cells are responding to different types of events. And so you immediately already know that the basic cartoon of dopamine is not right, because in the basic cartoon, all dopamine cells respond whenever the expected future value changes. Okay, so this is breaking it. So the easy interpretation of why it's breaking it is it isn't updating a scalar value prediction. Instead, each of these cells is learning about a different thing. And so here's a way of adjusting this model to think about that. Instead of one overall state describing now, and that being learnt about in the stratum and the prediction error system and the dopamine system, instead of that, you can rewrite it a bit like this. Multiple features of the world described now, and each of these features independently learns a different value, and each has its own prediction error. And actually, Rachel Lee and Nathaniel Dorr have done some lovely modelling of this, showing that this kind of model really does account for the data very well. Okay, so you end up with a situation like this, where independently we have like some circuits saying, does this whisker movement predict reward? And other circuits saying, does this left pillar predict reward, for example? And that fits in pretty nicely with things that we know about the anatomy of the cortical striatal system. So, for example, we have here are some connection diagrams showing that different cortical regions connect to different regions in the striatum. And then in separate studies, Suzanne Haber's lab have shown that different striatal regions have these loops with different regions in the dopamine system. So you can see these perfect. You can see a anatomical substrate for these self-contained loops, learning loops, a bit like it looks like in the dopamine data. Okay, cool. So overall, I've told you about dopamine, that really in the future we're going to be thinking about population codes. Dopamine is learning a distribution of values, and it's predicted by many different features of the world. What I haven't told you is various. There are many other puzzles whereby dopamine doesn't look quite like a reward prediction error. So, for example, dopamine cells routinely fire to surprises that are not obviously about reward, and you can cause with optogenetics, you can cause sensory as well as reward conditioning by stimulating dopamine. And so there's all sorts of fun stuff to be had with sensory learning, I think, in the future. And you want to look at Mel Sharp and Yael Neve and Jeff Schoenbaum's work for that. And then there's a series of nice papers talking about what dopamine neurons do in early phases of training, which needs some more thought before we can account for them in the simple prediction error framework. Okay, so that's what I'm going to tell you about dopamine. And now I'm going to concentrate more about this interesting question about what's up at the top. What is it that we should be learning about? And so in that previous task, the pillars task, it looked like dopamine was learning about everything. It was learning even about the basic sensory motor elements of the task. And this is like obviously absolutely fine if you're going to do the same thing a million times. It's like cheating. You can see that if a green pixel does tell you which way you should go, then you should learn from it. But that sort of strategy is not going to do well if even basic features of the task change, if in a world where that green pixel isn't there. And so are there cleverer, more structured representations around in the brain? And if so, where are they? So firstly, it's worth thinking about what these things need, what properties these things need to have. And so this is how we think about state representations in reinforcement learning at the moment. Here's a state representation, a mouse trying to go down one arm of this Y maze to get a reward. And he's at the start, and he gets the reward, and the next thing he's going to do is learn by temporal difference, that this previous state is valuable. And then he's going to do a new trial, so it still doesn't know anything about this bottom state, the important state for making the decision. Another trial goes by, and the reward back propagates another state. And so we're getting a little bit closer, but we still don't know anything about the bottom guy. Here's another trial, and only after the fifth reward will it back propagate all the way to the back and say, okay, I should go left. So this is not a good representation of the task, I would say. Because instead of that, if we'd chosen a different way of representing our tasks, we could have learnt about this in just one trial. Here, for example, if I'd had a representation of my task which had said, look, I'm in the left arm, rather than I'm at a particular state, then if I get one reward there, then I can immediately know to go to the left arm next time round. And similarly, in complex environments like houses, if you have a representation of where the rooms are, then you can do a much faster learning job than if you have to represent each piece of a room separately. So we need a complex map. We need a map of state space that has these kind of structures in them that help with learning. Okay, so where are we going to go looking for maps? And a good place to think about is for looking for maps is the hippocampal system, because they famously encode maps of space. Here's the hippocampus and entorhinal cortex in a rat and a human. And if you go and look in the hippocampus, you can find these things called place cells. These things fire at particular places in the environment. And then these things in the entorhinal cortex called grid cells, which seem to know the relationship between different places, because they fire along like grid lines through the environment that happen to be hexagonal. Okay, cool. So these guys are famous for having a map of space, but also they seem to know things about the task. Oh, actually, they're famous for having a map of space, but it turns out that these cells seem to do similar things in non-spatial worlds. So here is some of those place cells and some of those grid cells that you've seen before, and and now it's mapping out a one-dimensional rather than a two-dimensional world. But the amazing thing is this isn't a one-dimensional spatial world. This is a one-dimensional world in sound frequency. This rat is just listening to a sound which is going woo, woo, changing its frequency like that. And it has place cells in its hippocampus for where it is in frequency space, and things in the grid cell, in the entorhinal cortex, that might end up looking like grid cells if you were in 2 dimensions. So that's pretty cool. And we've shown these grid-like responses in humans. These aren't cellular recordings, they're fMRI recordings, but grid cells give this beautiful smoke signal out in fMRI that you can use. And we found this smoke signal in very non-spatial worlds. And so these are two-dimensional problems, abstract two-dimensional problems, such as mapping out the length of the neck and the legs of birds. So it looks like place cells and grid cells, the hippocampal map can work in non-spatial maps as well as spatial maps. And furthermore, it looks like the map that they form is not just non-spatial, but it's structured. It's optimized for the task. Here's one of those T mazes again, and some cells recorded. And if you look at this cell up here, these guys are place cells, right? They only fire in one place, just like the place cells did before. But this guy only fires when you're going to go left, and this guy only fires when you're going to go right. These are called splitter cells. And they're beginning to look like this kind of thing, a map of whether you're going to be in the left arm or the right arm of the maze. So this is something like evidence for what you might call a structured map of state space, the kind of thing we were looking for before. Here's another example, one of my favorites, showing a map of the task. Here's a mouse running in a maze, a circular maze. But the critical thing is he has to run 4 laps of this maze before he gets a reward. This is a beautiful study by Chen Sun. And you can see what the cells do. There are some place cells up here that always fire at the same point of each lap. But there are other cells that know about the task, not about space. And so these cells, for example, only fire on the first lap. And these cells count up towards getting a reward. They only fire on one physical part of space, but they don't fire much on the first lap. They fire more on the second lap, more on the third lap, and more on the fourth lap, as if they're building up activity towards the reward. Overall, they're forming a structured map of the task. Cool. Okay, so it looks like hippocampus has got some interesting representations if we're interested in a structured map of the task. But also parts of the frontal cortex do. And so here's some work from Yale Neve doing a very interesting reinforcement learning problem where with this rather complicated state space that you can see here. And this state space is where you are in this state space is represented in the orbitofrontal cortex or the ventromedial prefrontal cortex. At every point in that state space, you can decode where you are. And there's a whole series of beautiful papers by Yale arguing that the orbitofrontal cortex has a structured map of state space as well. And indeed, you can see here, I showed you from that grid cell study, that this same part of the orbitofrontal cortex does seem to have these grid-like representations, which could be a basis for a map. Okay, cool. So there's candidate brain areas for representing a structured map of the task. Hippocampus, for example, entorhinal cortex, ventral frontal cortex. But how do we think about this stuff mathematically? Well, this is an area of active research. There's lots of current ideas, but here's a good one. This morning, you've learned about 2 things. You've learned about model-free learning that takes a state space and just learns the values of each of the states. And you've also learned about model-based learning that knows the one-step transitions between each of the states, so that it can simulate a path through the state space to do planning. This is extremely expensive, but always works in the end. Well, what if we could get most of the benefits of that model-based learning, but without the requirement for that expensive simulation? What if we just stored where each state would lead to on average? So I could store, for example, where will I end up on average from this state? Or where will I end up on average from this state, etc., for all the states? That seems like the bones of a representation of a map. Okay, so this turns out to be really useful. You've learnt this morning that the value is the sum of expected discounted future reward. Well, it turns out you can just factorize that as the sum of expected discounted future state visits times the reward at each state. And this thing here is called the successor representation, and it's exactly what I've just told you about. So that thing is useful because it lets you separate out the structure of the word or the structure of the task from the reward, and you don't have to relearn this when the reward moves around. It's useful also because it gives you a nice way of thinking about clustering states together. States that predict the same futures cluster together, and that will give you properties like these arms of the maze. So that will give you good generalization properties. How would you go about representing these things in cells? Well, you could play it simple and say each cell predicts a different state. That's fine. This is what a cell would look like here. This cell predicts this state, and so when you're here, it's likely that you'll be here in the future, and so it should fire. And when you're over here, it's likely you'll be in the future. Here, you'll be here in the future, and so it should fire. This is looking a little bit like a place cell. But if this is an SR cell and not a place cell, you should be able to play some games. For example, if the mouse only ever walks in this direction, then these locations predict this state. These light locations predict this purple state, but the ones on the right don't, because it never runs that way. And so now you should get more firing on the left and less on the right. And indeed, of course, I wouldn't be telling you, but if not, but this happens. If you take a hippocampal cell that fires here, and then you train a mouse just to run left to right, you see the spreading of the place field to the places which predict the original place field. And it turns out that if you go and read Kim Stackenfeld's paper and Evan Rusek and Ida Menajad's papers, that these ideas explain a large number of effects in human behavior and in hippocampal responses. Okay, and not just hippocampus. Look at this equation here that I was telling you before, the sum of expected discounted future state visits. Well, this discount factor in SR is exactly the same as the discount factor that you've learnt about this morning already in RL. It tells you how far in the future you're averaging over. And Eva Brunek and Ida Menajad had a really interesting idea about the differences between the hippocampal and those frontal cognitive maps that are basically about how far in the future that you might be predicting, how much are you abstracting over the future. And so they would suggest, for example, that as you move from posterior to anterior, in the posterior parts, you're predicting the immediate sensory future, and in the anterior parts, you're predicting the long distance future, like your current goals. And so they had a lovely way of testing this because they had humans running through real virtual reality environments, and then they can compute the correlations between different immediate futures and between different far distant futures, and you could say, well, which correlation structure is better predicting fMRI data? And these are the kinds of things they find, exactly as predicted, that as you move anterior in the hippocampus and even more anterior in frontal cortex, you're predicting longer and longer, further and further into the future, longer and longer horizons. Cool. And so I think there's a whole bunch of exciting questions about what other differences there are between the frontal and hippocampal maps. Okay, so I've told you how you should represent those states, or one idea about how you should represent those states. But what about which states should I represent in the first place? And again, we can fall back on prediction. Instead of saying, well, choose a representation type which helps us do prediction, I can say, well, actually, I need to choose states which maximize the amount of the future I can predict. Well, let's think about that now. Let's think about it in this task here, this old T-maze task, but now a different version of it where the reward moves from side to side on each trial. It's called an alternation task. If I just have a place cell representation here, I know where I am in physical space, but I can never know where I am in the task. I'm going to get lost in the task because this cell is going to be active whether I'm going left or whether I'm going right. Whether I went left last time and whether I went right last time. So I'm never going to know where I am in this alternation task. Well, but whereas if we have these splitter cells, which I showed you earlier, which were in fact recorded from this exact task, now I'm good. Now I've got a separate representation for when I take this guy, and so I know the next one is going to go right, and a separate representation when I go that guy. And so I have to build a new representation which allows me to predict the two different futures. Okay, and so it turns out that that if you use this kind of argument, maximize the amount of future you predict, you can do a good job in lots of different tasks. Here's another one. This is a demonstration by James Whittington in my lab, which shows that by maximizing the amount of future you can predict in this Sunitel task, where they had to run around the lap 4 times, you can predict the exact representation that you see in the rodents. Cells that know where they are in space because they have to predict the immediate future, and cells that know where they are on the lap because they have to, which lap they're on, because they have to know to move to different parts of the space on each lap so that they can predict the long-term reward. That's exactly as I've shown you already. That's what the cells look like in the hippocampus. Okay, so I think there's loads of fun directions in the future for other good, efficient representations and working out how these things work. Okay, cool. So I've told you about what that state representation should look like, but I haven't told you much about how you can get it. And so to study that problem, I'm going to talk to you about generalization. How do you get that state representation? Well, we could just learn it from experience, but doing that is not much more use than having a rubbish state representation that I was talking about at the very start. You'd never be able to do anything first time because instead of learning reward, you'd first have to learn your state representation. So, okay, maybe instead of that, we can use pieces of other tasks. We can generalize it from other similar tasks. And it turns out you can. Here's a nice study showing that in reinforcement learning called meta-reinforcement learning. And the idea is you can train on many tasks of the same structure, but different sensory properties, for example, with boring old model-free learning. But what you're training is the dynamics of a neural network. And the dynamics of the neural network are going to learn stuff about that structure, the task structure. And then you're going to give it a new version of the task with a new sensory properties it's never seen before. And you can even turn off this model-free learning. And this guy here, the neural network, is going to instantiate its own learning algorithm. It's going to have learned how to learn. And in learning how to learn, it's going to have learned the particularities of the structure of that task. And so it's going to learn how to learn really well, much better than the original reinforcement learning algorithm that you trained it with. And it turns out it does that very well across a whole number of examples, but this is a particularly cool one because it was trained with a model-free learning algorithm I showed you here, but it encodes here in these network weights, it encodes a model-based learning algorithm, and this is the classic signature in neuroscience of a model-based learning algorithm. You may have seen it this morning. I'm not going to explain it in detail, but what this shows is that they understand this complicated state space of the task. Okay, so that's meta-reinforcement learning. I'm not going to spend much time about that because in some sense it's cheating. Because it is true that it generalized across different sensory examples, but we basically gave it the exact same task. What we'd like, and what nobody has yet, is something that can construct a task out of lots of different pieces of what it's experienced in different situations, so that it can immediately make a state space of a task for the first time. We need some kind of basis set for building state spaces. And this would be a really cool thing if you guys can solve this over the next few years. Well, let's think about spatial tasks. Spatial tasks mostly look a bit like this. Surely, if we're walking around in space, where in any particular environment, we still want a sort of basic representation of what spatial tasks look like. But of course, in different environments, you need to sort of nudge that representation in different ways. Can we just add some stuff to account for the fact that some environments have walls here, and some environments have walls there? If we can just add and subtract some bits, that's looking like a basis representation. And similarly, if shiny objects appear in the world and make us move towards them, they change the transition structure of our world. Can we just add some stuff to change our basic 2D representation into this new representation with different transition probabilities? Well, it turns out we can. What's the simplest basis representation for this kind of 2D-ness? Well, it turns out it looks like this. Either if you take the eigenvectors of this transition matrix, or if you compress this thing with a neural network, the simplest basis we can get looks like these grid cells that we were recording in the entorhinal cortex. So that's really promising. What about this guy? What's the simplest representation? Well, James Whittington can tell you what the optimal representation is for these kinds of nudging around with these wall cells, and they look like cells that fire preferentially along the boundaries or particular vectors to the boundaries. And in fact, and these cells are also found in that entorhinal cortex. And what about this guy? Well, the optimal representation for nudging around this guy are cells that fire at particular vectors away from these objects. Here's a cell here that fires 4 pixels to the north of this object, and here's another one that fires 5 pixels to the east. And this again is in James Whittington's neural network model, showing you what the optimal basis will look like. But if you go and look in the actual cells, you find exactly these cells that fire particular vectors away from the objects. And so it looks like, at least for spatial worlds, these kind of basis representations exist. And it'll be really interesting to see in the frontal cortices whether these basis representations exist for these more complicated non-spatial tasks we're worried about. Cool. So that was all I was really going to tell you about. I would love to talk about replay. I'd love to tell you some lovely stuff from Sam Gershman about state abstraction, and some cool things that are happening in the International Brain Lab, where you have so much data about what the animal has seen about the task, because they're recording video from absolutely everything the animal is doing. And so maybe it's possible to learn state spaces directly from the sensory input. Those kinds of things are going to be fun in the future as well. Great, and thanks very much to everyone that's contributed slides for this talk, and thank you very much for giving me your time and patience and putting up with me. Cheers, thank you.